Have you applied concurrency in your app, but you're experiencing on-the-side behaviors? Hey, my name is Dan.
And I'm Ignacio.
In this video, we're going to resolve four kinds of concurrency challenges that might occur in your production app by applying Swift Concurrency and simulating an IoT pet project. Here's a simple app simulating an IoT project, where the switch controls the light bulbs is on or is off states. If we tap the switch quickly, we will get undesired states. This issue might be simple, but it involves data races, main thread issues, reentrancy issues, and order of operations. We will explain these issues individually, starting with data races and how to detect them using the Thread Sanitizer tool.
Let's start with the first challenge. In the lightbulb class, we can see that the isOn state is directly accessed and modified in the toggle function. The problem here is that the isOn property is not thread safe. If multiple threads call toggle simultaneously, it could lead to a data race where two threads read and write the isOn value. For example, when one thread toggles the light state, another thread might be trying to read or write the same isOn value, causing unpredictable behavior. We can use the Thread Sanitizer tool from Xcode to detect this issue, which will warn us about unsafe access to share multiple state. To enable Thread Sanitizer, let's go to the Scheme menu in Xcode, click on Edit Scheme, then navigate to the Diagnostic tab, and from there, check the box for Thread Sanitizer. Once enabled, run the app as usual, and Thread Sanitizer will automatically detect any threading issues. Now, when we run this code, it will highlight the warnings related to isOn, confirming the presence of a potential data race. Let's check this out.
As we can see, Xcode highlights a data race in the line where the isOn store property is being modified. If we check the debug console, we can see exactly what's happening. As we can see, the thread sanitizer shows a problem where the memory is being written using the thread T14. At the same time, the same memory position is being read by another thread, causing a data race. We want to prevent data races to avoid on-the-side behaviors like invalid states.
So to solve this issue, we could use logs or dispatch queues, but it's simpler to use actors, a special type in Swift designed for concurrency safety. An actor is like a class, but with a significant difference. It protects its mutable properties from being accessed by multiple threads simultaneously. Using an actor ensures that only one task at a time can read or write to its properties. The actor automatically queues the access to its properties in the correct order, so everything happens sequentially and safely. Let's change the class keyword with actor keyword and then compile. We see a compiler issue. Let's take a look. It tells us that the expression is async, but it's not marked as await. This is because actors run in isolation, making their properties asynchronous as well. So we need to access them asynchronously by using the await keyword. Let's fix it and run again.
We have resolved the data race, but we now have identified a new data race issue. This one is located at the class named viewModel Now that we have detected a data race using the thread sanitizer and resolved it by using actors, we have yet encountered another threading problem, but in this case, in the view model. This data race happened because the toggle lightbulb function from the view model is scheduled concurrently twice by the app every time the user toggles the switch really quickly, causing the two threads to read and write at the same time from the viewModel is on store property. One way to resolve this problem is by making viewModel a main actor instead of an actor. This is because main actors schedule their async functions into the main thread while protecting their stored properties from data races. If we were to use the actor keyword for the viewModel class, then the UI wouldn't be notified from the current main thread, causing on-the-side behaviors in our app. Let's fix this issue by marking the viewModel with an add main actor annotation. If we run the app and hit toggle many times, we can see that the data race issues are gone. But then again, we still have a unsynchronization problem between the light bulb and the switch.
This unsynchronization problem between the light bulb and the switch happens because actors are designed to allow suspension points in their functions, which means they can handle other incoming tasks while waiting for an asynchronous operation to finish. This feature, called reentrancy, is usually helpful, but in this case, it's causing inconsistent behavior. To understand this better, let's see it in action with an animation. The first time we toggle the switch, a task is created and starts executing the toggle function inside the actor, with the isOn value in false state. At this point, the task is suspended while waiting for the light to toggle, and the actor is free to accept another task. If we toggle the switch again before the first task finishes, a second task is created. And since the first task hasn't yet completed, the second task will also start with the isOn value in false state. Now, here's the problem. Both tasks are running with the same state. So when the first task completes, it toggles the light to on. Then when the second task finishes, and it toggles the light again, but we will see no changes on the UI. This is because the second task overrides the changes from the first one, and we end up with an inconsistent state. Let's go back to the code. To fix this issue, we need to ensure that only one operation runs at a time in the actor. Instead of allowing tasks to overlap, we can block new tasks from being executed until the current one finishes. One way to do this is by adding a simple flag, like an isInProgress property inside the actor. This flag will let us track whether a task is currently running. When a task starts, we set isInProgress property to true, and when it finishes, we set it back to false. Also, before starting a new operation, we will check this flag. If a task is already in progress, we can prevent another from running until the current one completes. This effectively disables reentrancy for this specific case and ensures tasks are executed sequentially without overwriting each other. Let's try our solution by running the app.
If we hit the toggle twice, the breakpoint will stop at the return keyword from the guard statement, meaning the second operation will not run because the first one is in progress. Even though we have resolved the reentrancy problem, the switch toggle is not in sync with the light bulb because the second operation wasn't executed. Let's see what's happening first and then code a solution for this problem. When the user switches the toggle for the first time, the operation will be executed because no other operation is in progress. While a first operation is executing, a second operation won't be executed because the is in progress is on, not allowing other operations to be held for later execution. So while one operation is being executed, other operations coming from the user interaction will be lost. This is why we cannot synchronize states between the switch and the light bulb. So how can we hold operations as they come to keep the final state the user is expecting? One way is to queue operations as they come, execute them in batches, and use the final state as soon as they finish, while the first operation is being processed. The other operations will be queued. Let's see this in an animation. If the user toggles the switch, then a first task will be enqueued with the correct state is on false. As the user toggles again, the second task will be enqueued with the correct state because it waits for the first task to be completed. If the user toggles again, a third task will be enqueued with this on state to false because it will wait for the second task to be completed. Let's code this solution. The first thing is to enqueue the operations as they come. The function queue will receive an async operation that will be appended to an array of queues stored by the actor. Now we will await until each operation is executed asynchronously. While the queue is not empty, we will get the first operation and await until the next operation is finished. Once the queue is empty, the async function can return and continue the execution of the toggle function. Remember to avoid reentrancy problems by blocking the processing of the queue more than once. This is done by adding the is in progress check in the process queue async function. If we run the app, we can now see that no matter how often we switch the toggle, we always end up with the desired behavior. Okay, now Ignacio will give us the takeaways from the video.
In this video, we tackle 4 different challenges related to Swift concurrency, all within the context of our pet project. First, we saw how actors help eliminate data races by ensuring thread-safe access to shared properties. Then, we resolved the data races in the view model by using add_main_actor macro to ensure that all updates happen on the main thread. After that, we noticed how actors' reentrancy can lead to overlapping tasks and fix it by controlling task execution with a simple flag. Finally, we synchronized the switch and light bulb state by implementing a queue to process operations sequentially. By using Swift concurrency features like actors and the macro main actor, we were able to solve complex threading problems in a clean, structured way. If you found this helpful, don't forget to like and share. Thanks for watching and see you next time.
See ya.